Hello dear student, welcome to the session. In this session, we are going to discuss a small topic from magnetic effects of electric current. The topic is Biot-Savart's law. Yes, the starting topic of the chapter, and we have to see the applications of Biot-Savart's law, which is a very important topic for your entrance examinations. So shall we start? So first of all, let us see what is the statement of Biot-Savart's law. See here, I am considering a conductor which is carrying a current I. Okay, I am considering a very small elemental length from that conductor which can be denoted as dl. The term I into dl can be called as current element. Okay, now I am considering a particular point P which is at a distance of r from this current carrying conductor. Okay, and let this angle be theta. Then, according to the Biot-Savart's law, it states that the magnetic field produced at point P due to this current element, which can be denoted as dB, it is directly proportional to ideal, it is directly proportional to sine of the angle theta, and it is inversely proportional to the square of distance of the point from the conductor. Okay, so here we can give a proportionality constant K, which is mu 0 by 4 pi. So the equation becomes dB is equal to mu 0 by 4 pi into ideal sine theta divided by r square. And this mu 0 is nothing but permeability. Okay, and what's the value of mu 0? It is 4 pi into 10 raised to minus 7. So basically this is Biot-Savart law. Now the question comes from the application part. So let's see what are the different applications of Biot-Savart law. Okay, so let's move on to the first application. It is regarding a straight current carrying conductor. A straight current carrying conductor. Okay, and here we have to see 3 or 4 sub cases also. Let's see one by one. So, a straight current carrying conductor. Let's see the first case. We are considering that the conductor is of finite length. Okay, we are considering a current carrying conductor of finite length. See here. Okay, and this is carrying a current I. Now, we are considering the point P, which is at a distance r from the current carrying conductor, and by applying Biot-Savart law, we will get the equation of magnetic field at point P, and that is equal to mu 0 I by 4 pi r into sine phi 1 plus sine phi 2. This is the equation. Okay. So, you already know what is I and R. Now, what are the angles phi 1 and phi 2? See, these are the two finite ends of the conductor. I am just drawing a dotted line connecting the finite ends to point P. Okay, and these dotted lines are making these two angles with the vector R, isn't it? So, that angles can be denoted as phi 1 and phi 2. Okay. So, this is a very important equation. You have to by heart this equation. This is the equation to find the magnetic field due to a current carrying conductor of finite length. Now, suppose if you are considering a conductor having infinite length. So, let's see case B, where the current carrying conductor is an infinitely long current carrying conductor. Then what will be the values of phi 1 and phi 2? Yes, both will be equal to 90 degree, isn't it? If the conductor goes infinitely long like this, then definitely phi 1 and phi 2 will have their maximum values, which is equal to 90 degree, isn't it? Now, when you substitute the values of phi 1 and phi 2 in the above equation, you will get the value of magnetic field as mu 0 I divided by 2 pi r, isn't it? Because sine 90 plus sine 90, that is 1 plus 1, 2. And that 2 and this 4 will get cancelled, and finally you will get mu 0 I by 2 pi r. Clear? Now let's see the third case, which is also very important. See, here also we are considering a current carrying conductor which carries a current I. But here one end of the conductor is infinite and the other end is finite. And we are considering the point P near to the finite end at a distance r from the conductor. Now we are going to write the equation of magnetic field at point P as the same equation, mu 0 I divided by 4 pi r into sin phi 1 plus sin phi 2. So here what are the values of phi 1 and phi 2? Considering the infinitely long end, phi 1 will be 90 degree, isn't it? And considering the finite end, phi 2 will be nothing but 0. Okay, so you will get the equation as finally mu 0 I divided by 4 pi r. So this is also very important case. Okay, now the fourth case is if point P lie along the axis of the current carrying conductor. Okay, that means if point P is lying somewhere over here, okay, along the axis of the current carrying conductor or on the current carrying conductor, then what is the magnetic field? Yes, it will be definitely equal to 0 if the point P is lying along the axis of the current carrying conductor. Clear? So these are the four cases to be remembered regarding a straight current carrying conductor. Now let's move on to the next case, which is a circular loop which is carrying current. A circular loop. Okay. So let us consider a circular loop which is carrying a current I, and let us consider A as the radius of that circular loop. So here we have to by heart two equations. The first one is to find the magnetic field at a point on the axial line. See, this is the axis of the current carrying coil, and we are considering a point P which is at a distance x from the center of the coil. Okay, center of the loop. Now, what is the equation to find the magnetic field at point P? Yes, it is mu 0 IA square divided by 2 into a square plus x square the whole raised to 3 by 2. Okay. And here you have to by heart one more equation. If you are considering the point at the center of the circular loop. Okay. At the center of the circular loop. See, we can consider the point as point O. So what is the equation to find the magnetic field at point O? We know that definitely at the center of the circular loop, the value of x will be equal to 0, isn't it? So when you substitute for x as 0 in the above equation, you will get the expression as simply mu 0 I divided by 2a. And if you are considering a current carrying loop having n number of turns, you can rewrite the equation as mu 0 ni divided by 2a. Okay, clear. Now, if you are considering just an arc which is carrying a current I, and let us consider that this arc is subtending an angle theta and A is the radius of this sector. Okay, then the equation to find the magnetic field at point O is given by mu 0 I by 2A into theta by 360. So this is also a very important equation regarding a current carrying arc. Okay. And you can see a sector here. The arc is subtending an angle theta at the center of the sector, and this is the equation to find the magnetic field at the center O. Clear? Now let's discuss some questions from Biot-Savart Law. Let's see the first question. An infinite wire has a circular bend of radius A and carrying a current I as shown in the figure. The magnitude of magnetic field at the origin O of the arc is given by. See this figure. In this figure, we can consider the conductor as three sections. Okay, see here you can see a straight section and then an arc, again a straight section, isn't it? So, we have to find the resultant magnetic field at point O due to all these current carrying sections. Okay, to find the resultant, first of all, you have to find the directions in which these magnetic fields are acting. To find that direction, you can apply, yes, right and thumb rule. So, first of all, let us find out the directions of those magnetic fields. First, you consider this straight section. See here. You can see the direction in which current is flowing. So, just apply right and thumb rule over there. Then, what is the direction of magnetic field at point O? Just produced due to the straight current carrying section. Yes, it is pointing into the plane, right? Now you consider this arc, current carrying arc. There also you apply the right hand thumb rule. Yes, the magnetic field is again pointing into the plane, isn't it? Okay. So, consider the third section. Obvious. The magnetic field due to this section will be equal to 0, isn't it? Because point O is lying along the axis of this conductor. Okay, so we have to consider only just two magnetic fields. The magnetic field due to this straight section as well as the magnetic field due to this current carrying arc section. Okay, and by applying right hand thumb rule, we found that both the magnetic fields are acting into the plane of the screen. So we can just add up those two magnetic fields to find the resultant magnetic field at point O. Okay, so let us write the expression for the resultant magnetic field at point O. The first equation, yes, it is the magnetic field due to the arc section. What is the equation? Mu 0 I divided by 2a into theta by 360. See, what is the value of theta? Obvious, it is 270 degree, right? The angle subtended by that current carrying arc at point O is obviously 270 degree. So 270 divided by 360. Okay. Plus, now the magnetic field due to the current carrying straight conductor over here. Okay. You can see that for this conductor, one end is infinite and the other end is finite, and point O is near to the finite end. For this particular case, we have just seen an equation which is mu 0 I divided by 4 pi r, isn't it? Mu 0 I divided by 4 pi, here it is a in place of r. Okay, a is the distance of point O from this straight conductor. Okay, now 270 and 360 cancels, you will get 3 by 4 over here. Now take mu 0 I by 4a common from both the terms. Yes, you will get the first term as 3 by 2 and the second term as 1 by pi, isn't it? Now in all our given options we have pi also common outside. So just take pi also outside the bracket. Mu 0 I by 4 pi a into, yes, 3 by 2 divided by 1 by pi. Yes, you will get 3 pi by 2, isn't it? Yes. Plus the second term 1 by pi will become 1. You're taking 1 by pi common out from both the terms, isn't it? So, you are getting the answer for this question as option B, mu 0 I by 4 pi a into 3 pi by 2 plus 1. I hope the solution is clear. Now, shall we move on to the next question? Yes, read the second one. Two insulated circular loop A and B of radius A carrying a current of I in the anti-clockwise direction as shown in the figure. The magnitude of magnetic induction at the center will be. See, here we have two circular loops. Both are carrying the same current and both are having the same radius. Okay, and both the loops are carrying current in the anti-clockwise direction as shown in the figure. Okay, so we have to find the total magnetic field at the center. See, here you can observe that the planes of the loops are perpendicular to each other. Okay, loops are having perpendicular planes. So definitely the magnetic fields will be also acting in perpendicular directions, isn't it? If this is point O, then magnetic field due to the two loops will be acting in perpendicular directions like this. Okay. So, to find the resultant of two perpendicular vectors according to parallelogram law, we have the equation root of b1 square plus b2 square, isn't it? And here, what is the equation of B? We have to find the magnitude of magnetic induction at the center of the loop, which is the common center, isn't it? To find the magnetic field at the center, we have the equation mu 0 I divided by 2a. Here, both the loops are carrying the same current and both are having the same radius. So, I and A are same for both the loops. So, B will be also same. Okay, we can write B1 is equal to B2 is equal to B. Okay, so what is B total? It is root of b square plus b square, that is equal to root 2b. And what is the equation of b? It is mu 0 I by 2a. Okay, you can write this 2 as root 2 into root 2, so that 1 root 2 will get cancelled from numerator and denominator, and your final answer will be mu 0 I divided by root 2a. So the answer for this question is option B. Now read the third question. A long wire carrying a steady current is bent into a circular loop of 1 turn. The magnetic field at the center of the loop is B. It is then bent into a circular coil of n turns. The magnetic field at the center of this coil of n turns will be dash. So first of all, we are having a single turn circular loop which is carrying a certain current. Then what is the equation for magnetic field at the center of that circular loop? Yes, that is of course mu 0 I divided by 2a, isn't it? Now, it is given that the same wire is bent into a coil of n number of turns. In that case, what is the magnitude of magnetic field produced at the center of the coil? So, we can denote it as B dash. How will you write the equation of B dash? We are having n number of turns, isn't it? So, mu 0 Ni divided by, one more thing to be noted, you are bending the same wire into a coil of n turns. So, the radius of each turn will be 1 by nth of the previous value, isn't it? So, in place of a, you have to give a by n. So, this will give you n square times mu 0 I by 2a, which is equal to n square times the magnetic field at the center due to a coil of single turn. Okay, so the answer is option B. So, I hope the questions discussed in this session is clear to you. The concept of Biot-Savart law and its application is very important for your entrance examination. So, practice more questions from the equations connecting the straight conductor of both finite as well as infinite length, and one infinite and one and infinite, that's also very important case. Then circular loop, then current carrying arc, all these equations are very important. Okay. So, practice more and more questions from the topic. Hope you have enjoyed the session. Thank you.